Hey, it's Jonathan Broadwell, creator of the Serial Wombat open source project and an embedded systems consultant at my company, Broadwell Consulting Incorporated. If you need help with medical device development or an embedded systems project, look me up. Today we're going to be looking at another example of how the Serial Wombat 18AB chip can act as a real-time control coprocessor for your computer or Arduino chip or MicroPython system, or basically anything that can talk over UART or I2C and send out commands. Today we're going to be looking at controlling a wooden elevator that I got from AliExpress for a few bucks. It has a 3-volt motor on the top. Originally it had a couple of push buttons that made it go up or down, but I thought we can do better than that. Let's control it in real time. So we're going to control that motor with an hbridge, and we're going to throw an ultrasonic distance sensor in the bottom of the elevator shaft so we can see where the elevator's at. And then ultimately we'll use a keypad to command the elevator to go to the top floor, the middle floor, or the bottom floor, and use real-time control to get it there. Let's take a look at our physical plant. Okay, let's take a look at our physical plant. We've got the elevator assembly that I got for a few bucks off AliExpress. We've got the brushed motor on the top. That brushed motor is attached to an hbridge module, DRV8833, I believe. And that's being powered by a power supply of 2 AA batteries. We're using a separate power supply from our motor versus our electronics, which I always recommend. We've got an HC-SR04 Ultrasonic Distance Sensor, which will sense the distance from the sensor to the bottom of the elevator car. There's a limit on that sensor of around 4 centimeters, so we won't be able to come all the way down till we touch it. It needs a little bit of distance to do the ultrasonic sensor measuring. We're limited on the top by the string and the eye bolt. That we don't want that to hit the top of the elevator shaft. Over here we have a Serial Wombat 18AB chip hooked up via UART to my PC. Near the end of this example, we'll switch that over and run this thing off of Arduino. We've got a 16-key keypad that when we get to Arduino, we'll use to measure the elevator car, or to set the elevator car. We'll declare floors 1, 2, 3, and 4, and have the elevator go to those positions. We've got the HC-SR04 hooked up to pins 10 and 11. That's important because this is a 5-volt sensor running off the 5-volt supply, and we need that in order to be able to measure that. We go into one of the 5-volt tolerant pins on the Serial Wombat chip. We're running the H-bridge off of pins 0 and 1, which are both enhanced digital performance pins, which is good so that we can get high-res PWM. So that's about it for our physical plant. Let's run this thing and through the WombatPanel and characterize the system. Some of the code that you're seeing right now as of the end of February of 24 is pre-release. It includes features like the H-bridge that are going to be in version 2.1.2 of the firmware that is not out as of the time that this video is launched. So watch for my official 2.1.2 release. If not, you can get the code off of GitHub and build it yourself. I don't have pre-assembled hexes, and the latest version in a non-tagged manner is always at the lead of the GitHub repository for the C# library. So grab those if you want to play with them, or wait for the official release when everything's tested and ready to go. Let's take a look at how to control this thing through the WombatPanel application, which we will then use to automatically generate Arduino code. So we know we've got an ultrasonic sensor on pins 10 and 11. That one's real straightforward. We just use the normal sampling. And there we go. And we're seeing right now there's about 45 millimeters between the sensor and the bottom of the elevator car. Pins 0 and 1 are set up as an H-bridge. Let's configure that. And we see if we go to the left, the car goes down. If we go to the right, the car goes up. That works good. Then finally, we have a keypad on pins 12 through 19. And so you set up your columns and rows for the appropriate pins. If you look up above right here, there's a whole video on how to use the matrix keypad. It's a very capable thing, but we'll use it in its most basic form, where it's just going to queue up key presses and send them to the Arduino. So let's say configure and auto sample on that. Let's run a quick test. A 2, number 3 key, got a 3. So that is working very good. And we'll try PID control and see how that works for us. So let's go back to the ultrasonic distance sensor. For PID, typically I like to scale it from minimum to maximum. And we're going to have a minimum of 45 millimeters. There's a limit to how close you can get on the sensor before it stops working and it provides a really wacky value. And I know that the elevator car can go up so that the bottom's about 11.5 centimeters from the sensor. So we'll use those for our 2 input scalings. And we can see right off the bat, okay, we've transitioned now from 45 to 115 to 0 to 65, 535. As we get closer, we also see, boy, there's an awful lot of jitter in this signal. So that sensor is limited in its resolution, and also because the Serial Wombat chip detects in 17 microsecond intervals, there's also some quantization going on there. So let's go ahead and, I think for this one, filtered makes sense. We're going to want to control on this and maybe not aggregate a whole bunch of samples. So we'll put in a filter on this, and 65417 is a half hertz filter. 65298 is a 1 hertz filter. Let's put a 1 hertz filter on it, a 1 hertz cutoff. I'm sorry, maybe something, let's put a 5 hertz cutoff on it, 64358. So we will say set and enabled. And now we see, okay, now we're getting a much cleaner signal. So that'll help us from a controls point of view. So now let's go back to the hbridge, and we'll go to feedback control. The pin providing the input is on pin 10, and so we want that to be our input. We're going to use PID, and let's go to the show graphs page so that we get the good PID controller here. And we'll start with the KP at 256 and just see what that does for us. And our target value, and I have to enable the driver. So, and let's show the graphs. Okay, 256 is not enough to significantly move the controller. So let's double that. Okay. So we came down, that looks pretty good. And so now let's change the target value and let's set it up almost to the top. Now let's set it to the middle. And we got a lot of overshoot there. It did settle down, though. It did come back. So let's see if that's typical if we do it again. Yeah, a lot of overshoot. So that's not working real good for us because we're not getting good closing, and we're also doing a lot of overshoot. So that's not great. Let's adjust the pin period, just the sample period, to be more in line with what we're producing samples at with the filtering. And we'll try that again. So we can reduce this KP to try to get rid of that overshoot. But then we have a closing problem. And the way we deal with the closing problem then is with our integrator. So, and we'll see, that's not quite enough to get us closing our problem, closing our error. Enough. And then again, we got pretty massive overshoot. Part of the problem with this particular control system is that you have a long time, it takes a long time to move that elevator a distance compared to the response time of the system. So any kind of an I component is almost always going to have a overshoot to it. So at the end of the day, PID is just not a very good control system for this. So let's see what else we can do. I'm going to take the chip back here and run it through a reset. That will clear everything that we got going on. Configure. That gets us back, and okay, we're at about 25 millimeters. This time we're going to skip doing the transform on this thing, and we're just going to operate in millimeters because the hysteresis mode doesn't really need that concept of min-max. Hysteresis is what we're going to do to control it. Some people call that a bang-bang controller. So I'm going to hit this again and get that filtering in place. So we've got a nice smooth signal. Now let's go over to the hbridge again. We will configure that guy. I'm going to flip this off while I make changes. And on the feedback control, under hysteresis, let's shoot to raise the thing to 110. So if we're below 109, I'm going to give it full power up, 65,535. When we hit 110, I'm going to set it to 32,768. That's the middle value of our 65,535 swing. So all the way at 65,535, we're going up as fast as we can. At 0, we're going down as fast as we can. At 32,768, we're not going up or down. So let's configure the hysteresis, enable the controller. And what do we see? That's not good. So we'll configure the hysteresis controller and enable that guy. And up it goes, and it stopped, looks like a little bit above 110. So we know we still got a little bit of overshoot. Next time we're going to set it a little bit lower so it stops, it stops a little bit sooner. Okay, let's stop the video for a second and talk about what happened, why it went all the way to the top. In retrospect, that filter was getting in our way on the input scaling on the ultrasonic distance sensor input. The problem was we're only moving across a range of about 80. And so the filter, the change in was only moving by a few counts per sample. And that was actually falling off of the end of the filter. It never added it up enough to move the filter. And so it appeared as if the ultrasonic sensor was frozen. We'll talk about this again later at the end of the Arduino video. But in retrospect, we either needed to turn off filtering or maybe just average a few samples because the filter is not good at dealing with very small movements, which when we're not scaled up to 0 to 65,535, that's what this is. So back to the video. So our low limit and we'll turn it off this time at 62 on its way down. So it can cruise just a little bit. 32,768 is off. And above 62, 63 or higher, we're going to output 0, which will drive this thing down as fast as it can. So let's take again a look at our output. And are we doing a first order filter here? And we came down, and it looks like we wanted to hit 60, and it looks like we hit it just about on the nose. Let's go up to 90. So we'll shut it off at 87, because we saw we overshot last time. So at 86 or lower, full power up. At 87 or higher, the mid value, which shuts off the motor. So let's send it up to 90. We'll stop it at 87 and see if it overshoots. And we were shooting for 90, and we got very, very close. So this hysteresis is definitely how we want to try to control this. And what we'll have to do on the Serial Wombat chip is, on the Arduino, is send a new hysteresis control each time we want to move the elevator up or down. But we'll rely on the Serial Wombat chip to actually do the control and get it to its desired position. So let's now generate some code. So what I have here is an Arduino sketch that I created, and I created a little framework for myself, include serialwombat.h, declare a Serial Wombat chip, wire begin, which gets our I2C, serial begin, which lets us write things out to the terminal, and Serial Wombat begin on wire at address 0x6b. We're going to use the default address with no jumper when we do this. So now let's go back to the WombatPanel application. And I don't yet have automatic generation code for the ultrasonic distance sensor, which is not a huge problem. This is not a huge problem because if you go to serialwombat.com, go to docs and links, we can come down here and go to the Arduino library. I'll go to my class list and pick the ultrasonic distance sensor. And what do I have to do? Okay, I got to declare a Serial Wombat sensor on the serial, attached to the Serial Wombat chip. And let's copy over the begin. We know we got to initialize that guy. The echo pin is on 10. The trigger pin is on 11. Auto trigger true, pull up false. That all looks good. And what driver are we using? We're using the HC-SR04. So that will initialize our distance sensor. The code generation is a work in progress on the WombatPanel. Make sure that you've grabbed the latest WombatPanel. You can look up above for an overview of this particular application. And let's grab our matrix keypad. That gen code is fully functional at this point. And it creates automatically generated commented code. And one of the things on the comments is it says, put this line before setup. You have to do that. Makes it easy to put it all in one cut and paste, but we got to get the initializations, the declarations up above setup. Now let's set up our hbridge. And so we'll say gen code on this one, gen code on that one, and gen code on that one. This one clears the clipboard, these two append to it. And so this will set up our hbridge and set up the hysteresis at the beginning. For this first one, we're going to tell it 32768 no matter what, okay? Because when we first come through here, we want this thing turned off. Now, we'll put a delay in here of 500 milliseconds. That will allow the ultrasonic distance sensor to get some signals under its belt. And then let's define 3 locations. The top floor is a distance of 110 millimeters. The mid-floor is 80 millimeters. And the bottom floor is 50 millimeters. And so right off the bat, we're going to tell it, okay, if distance sensor got read public data is greater than bottom floor, then we're going to set up our hysteresis to make the thing go down. And what we're shooting for is to make it go down. If it's above a value, we're going to set the output to 0. And bottom floor. And the low limit where we're going to shut it off is bottom floor plus 2. And that should drive it all the way to the bottom floor. Now, for the loop, let's int 16ti equals, and we'll read a value off the keypad. And we're reading an int 16 there. It'll return a -1 if there's nothing to read. So we'll do a switch on I. If they push button 1, case 2, go to middle floor. Case 3, go to top floor. And so for this one, if the distance sensor, we already know how to go to the bottom floor. And if it's not already above, if it's not above, it might be below. So in this case, if it's below, we want it to go up. From -2, and the high limit will be 65, 5, -3, bottom floor -2, and the high value will be 32,768. And let's give that a pound. Let's give that a pound to find. Okay, if we want to go to the middle floor, essentially it's this same algorithm. Do we call that, yeah, mid floor? And we're cutting and pasting a lot of code, which to me says this could be refactored, probably into making this one routine thing. But for the purpose of this demonstration, since I'm coding on the fly, we're not going to worry about that too much. Okay. And then now since we did all that automatic code formatting, let's go up to Sketch, Tools, Auto Format. And it looks like we got an extra brace in there. And I 0 print we'll print out a button every time we get it, just so that we're getting the button pushes. Let's verify that. Okay, we're going to see the code load all the way up. And the first thing it does is it drops the elevator to the first floor and stops, then waits for a button push. I'm going to push number 2. And it goes up to floor number 2. I'm going to push number 3. And it goes up to number 3. I'm going to push number 1. And it goes down to floor number 1. So a couple of things to notice as I was doing this. I kind of make these demos on the fly, and so I don't always know exactly how they're going to turn out. First of all, I added some extra wires longer to get the H-bridge and the motor wires away from the Serial Wombat chip in the Arduino. I was getting lockups as the result of all the magnetic fields that were created. Secondly, it turns out that when you're using numbers that only change by 1 or 2, the filtering algorithm is not a good one to use. So I took that out, and you see this thing, it'll glitch a little bit. But as a result, the filter sometimes, if you're only moving by 1 or 2 counts, that will end up in the round-off error. And so it was not detecting the fact that the thing was moving and I was hitting the top of the elevator tower. So that's not good. So for small values, go with an average. For larger moving values, go with a filter. And this is especially true if you're using heavy filter constants. So, and we can see, we're still doing real-time control. If I put my fingers in here, it tries to compensate. And if I push the up button, and my little string is slipping here. There we go. It goes up and stopped. So, and we can see again, it managed to control even though the string was slipping. It is definitely a closed loop system. So now let's just real quick review everything that we configured in this project. We started with the HC-SR04 Ultrasonic Distance Sensor. We hooked that up to pins 10 and 11 because these are 5-volt pins. This sensor requires 5 volts to run, and the echo response that it comes back is a 5-volt input, so it has to go to one of these yellow pins right here. So that creates, we configured the ultrasonic pin mode, which creates the trigger pulses and reads the response that comes back, then converts that via time of flight of sound into millimeters. That set of millimeters goes into the input processing block for pin number 10. We ultimately decided that we didn't need the filtering or averaging that we were able to do without it. We did experiment with it a little bit earlier when we were feeding it into the PID. So that travels from the pin 10 input processing. Pin 0, which is our H-bridge pin mode, was configured to listen to pin 10 for its input. So it pulled that data and brought it in. We didn't end up scaling it. We used it in its inherent millimeters. We didn't have to invert it. Our control feedback was hysteresis, although we ended up controlling it dynamically from the Arduino, changing the control algorithm as needed to move it up or down based on our needs. We didn't use the timeout fault. We didn't end up averaging or filtering the output or scaling it. So then we sent out a value that at any given time was either 0, 32,768, or 65,535 to the H-bridge pin mode. And it took that and either pulsed pin 0 or pulsed pin 1 with a PWM and set the other pin low. The H-bridge pin mode therefore uses 2 pins to output direction and power. That went to the DRV8833 H-bridge module, a FET-based module, that was controlling the elevator motor. It got its power from a 3.3 volt battery. We noted that we had to be careful to keep this far away enough from our other electronics that those wires didn't transmit enough noise to mess us up. Finally, our user interface was a 4x4 matrix keypad. We hooked that up to 8 pins on the Serial Wombat chip, and enabled matrix keypad mode in all of its default configurations. And this stored data that came in a queue until it was asked for either by the computer over UART or over I2C from the Arduino. So that was the configuration of our system for this project. You can find the code that goes with this in the examples under YouTube Elevator Controller in a future release of the Arduino code base that goes with version 2.1.2 of the Serial Wombat 18AB chip firmware. So I hope you enjoyed this demonstration and saw a little bit about how we can generate code. If you have any questions or comments, please leave them down below, like this video, and subscribe to my channel. I'm moving slowly towards being able to get a little bit of money, probably nickels and dimes from YouTube from the views, but I got to get some more subscribers to get there. So if you've been vacillating about subscribing, please do that. And that's about all I have for now. Have fun, keep making stuff.
The Serial Wombat firmware is available on GitHub and is constantly being updated. Subscribe below so that you can see the latest features and videos that come out as we fix bugs and add new features. The Serial Wombat open source project was created by Broadwell Consulting Incorporated. Broadwell Consulting Incorporated provides help developing medical devices with a focus on developing embedded firmware, which is compliant with IEC 62304, ISO 14971, and ISO 13485. as well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting. Support requests for Serial Wombat should be sent to help@serialwombat.com and will be answered on an as-available basis. Also, feel free to leave your question in the comments below.